I'm Simeonov. I'm the founder and CTO of Swoop. It's a company you probably never heard of because we do some very niche things. In some ways, we're very similar to Google because we do performance advertising. And we actually built the company using insights from Google, except that since we decided not to build another search engine, we do what Google does, which is search advertising, but we can do it in content. It's a very interesting problem, and it's very different than the ones that we so far talked about, because it actually deals with human decisions. And the hardest thing about a human decision is that you have no counterfactual evidence. You know what a human did in the particular situation, but you have absolutely no idea what a human would have done if the situation were different. You could reason statistically about it, but there's absolutely no way ever to know. And that makes things very, very difficult. Performance advertising is a very, very competitive world, and absolutely nobody beats Google. Nobody beats Google because we go to Google search and type in a query and we have a very specific and immediate problem. The fact that we perform very close to Google, as measured by third parties, based on offline result by identified humans, sort of about the most precise measure you can have, and about 5 times better than other forms of advertising, suggests that we are doing something really interesting with our systems. And it's definitely not because we're smarter than most other people in ad tech. It's not because we spend more money on it or have larger teams. We think to a large extent it has to do with the way we think about optimizing the use of data science to achieve business needs, specifically in human decision systems. So the basic problem here is that you have users who visit pages and you want to show them ads. By the way, almost all advertising on the internet is absolutely horrible and useless, though I would argue that the ads on Google search result pages are quite valuable. Our ads are like that. And the performance based on user actions actually proves it. It's valuable content. So you need to make some predictions in order to make some decisions. The basic decision is what ad to show. The complexity here is that you have a feedback loop. The decisions you make affect the future choices you're going to have. People stop there. The most important insight that comes from Google is they also affect the humans and how humans will react to choices you present to them in the future. The biggest reason why search ads on Google perform so well is actually not because we type in a query and we're in search mode. I can talk to you for 2 hours about the data behind that. The biggest reason is they have performed well since about 2000 when Google AdWords launched. And it had simple, readable, relevant ads. So we actually have a positive feedback loop. We learn to treat the ads on Google search result pages as content. And sometimes the very same ads in Google AdSense, far worse targeted on content pages, we treat as crap. Most of us have ad blockers running. I do, even though I'm in ad tech. And I have disabled my ad blocker for Google Ads on search result pages, but I'm actually blocking many other ad networks. I find value in the ads from Google. I don't find value in the ads from other networks. The reality actually is a lot more complicated than the simplified picture. You actually have to make many predictions to make many decisions. And independently, code, remember code is law, code makes a whole bunch of implicit decisions by the nature of whatever it is or the data that's fed to it. They're all mangled together to affect the system. And meanwhile, the world is changing. You don't get all the data. Obviously, you don't have counterfactual evidence. You're in a semi-adversarial environment. There's internal competition between multiple objectives by different advertisers, different campaigns. It is a wonderfully nasty mess. It is absolute fun to do machine learning and data science on. And you do this at petabyte data scales. The insight I want to give here, and maybe it's because I'm not a data scientist, I'm a computer scientist and an economist and a former venture capitalist and a founder of many companies and an angel investor. So I think of data science as startup investing. And by the end of this talk, I hope all of you are going to think of yourself as investors. And that, to me, is the reason why we perform so well relative to other people in ad tech. Here's the general analogy that I draw. An opportunity is essentially something that you can solve. Right? Due diligence, the process of choosing whether to make a decision, is selection, evaluation, training. Making an investment is the equivalent of giving something production bandwidth. Making a follow-on investment is equivalent to keeping something running in production because there's an opportunity cost from running something else. Right? There's a limited production testing bandwidth, even if you do multivariate testing. Managing your investment portfolio is optimization across various predictions and decisions that result from them across the entire system to achieve a business objective, not an ML evaluation objective. There are no papers here to be written. And the reason why the title of the talk is Buzzword Noncompliant is because I don't think a paper will ever be written about any of this. But our company is very profitable and growing very fast in an industry where most companies that are not called Google or Facebook are doing actually quite poorly. The ultimate return is the business impact you create. So this really is a portfolio optimization problem, right? You have limited resources and some amount of time. You need to deploy your resources in order to maximize the net present value of your return. Impact and return sooner is more valuable than impact and return later, right? And the trick is that you're dealing with a non-stationary distribution, the world is changing, that is insanely skewed. How skewed? Well, the insight from data science is we know that it's very difficult to predict the marginal value of the next hour of data science work. In fact, we know that many of our experiments, be it on feature engineering, model deployment, result in zero value. They make no change, or they actually do a worse change. But we do know that somewhere out there, there's something really, really cool we can do that will radically change things, that will radically improve things. And in the earlier talk, you saw the jump with convolutional neural networks, for example. It led to a radical improvement in accuracy. It was a leap, right? A while back, years ago, I did some analysis of angel investment portfolios. I got some data, and the summary was that on average, investors got 3.2x cash-on-cash return. If you put $1 million in, you get 3.2 million bucks out. However, 45% of investors got zero out. They lost all their money. And 66% of investors lost some money. So we're talking about a distribution where the mean is 3.2 and the median is very, very close to zero. I would argue the distribution of return from data science work looks something like that. It is extremely skewed. Most data science work doesn't generate value. The reason why we do data science work is because we know that in a situation like that, if we pull enough times from the distribution, we will land something on the long tail and will create significant impact. So how do we think about operating in this environment? Well, what people have learned about investments, which I've done for many, many decades, is that there are a few key return drivers. The most important one is to not be pulling from the distribution that everybody else is pulling, to somehow skew the distribution in your favor. So you invest in building your own deal flow, in both in greater quantity and greater quality than all the other investors. You figure out how to make your capital give you more shots on goal. If you have $100 million to invest, and you invest in companies that take $10 million in their life cycle, then you can only invest in 10 companies with a highly skewed distribution that is not enough to get you a return that's close to the mean. If you invest in companies that on average take $1 million, they'll give you 100 shots on goal. That gives you a much higher likelihood of achieving the mean return. And ultimately, you need to develop some ability to pick winners. A due diligence process, some insight, industry knowledge, connections, personal experience, whatever. But you're going to have many more choices, many more things you can train, many more things you can deploy than you have resources to invest in. So you're going to need to select, right? Let's look at some of these. So data creates opportunities. And again, you need both quantity and you need quality. This is a simple ad tech example. This is the simplification of the advertising value chain. It is insanely complicated. And you're talking about many tens of billions of dollars, and everybody's trying to figure out how to get a piece of the pie. So what you have here is a whole bunch of companies that only see a portion of what happens. Many, many point-to-point integrations. It leads to a limited set of data that they have access to. On the other hand, both Google and we, following Google's example, built end-to-end systems that go from publishers, where users are, all the way to advertisers. Right? That results in lots of data, and that data fundamentally allows you to do things that others in the industry can't even dream about. You have a richer signal, so you can provide new inputs to models. You also have a cleaner signal, which the more sophisticated your models becomes very, very important. Simplest example I can give you here is that in a typical ad network, it's not clear whether the user actually viewed your ad. It's pretty clear that you delivered your ad, but not very. It maybe even is possible to know that some portion of the ad was in the viewport, but were the user's eyes actually on it? Was it fully in the viewport? How long did the user spend on that? Were they scrolling right through? You don't have that signal. Google does. We do. So imagine trying to build a click classifier and not really knowing whether your no-clicks actual no-clicks or whether they're just no-ops, a tree that fell in the forest and nobody was there. The user wasn't even paying attention. How can you evaluate a decision? Maybe if the user paid attention, maybe the ad was fully in the viewport and didn't just scroll through in 1.3 seconds, the user would have clicked on it, right? One more point. You can see both sides of the auction, right? The goal here is to actually optimize the marketplace, balance supply and demand. There are conflicting goals between users, publishers, advertisers, the operator of the marketplace. And if you don't see both sides of the marketplace, it's extremely difficult to be able to execute in a manner that satisfies the conflicting objectives of all the parties. But if you do, you actually may be able to do it. Not perfectly, but you at least have a chance. So data creates opportunities, and the insight I want to leave you with here is we are trained, especially those of us who have been through some form of academic training around data. For me, it was econometrics, part of my economics degree. We are trained to take data as a given. You know, governments produce data. Here it is. There's nothing you can do about it. Kaggle trains people. Here's your data. There's nothing you can do about it. This is bullshit. It may be expensive, it may be difficult, but you can create your own data. The previous talk showed it, right? The team had very, very innovative ways to actually get the data they needed at probably reasonable cost, right? So the starting point is don't take the box you're in for granted. The first thing you should be thinking about how to get outside the box and gain access to more opportunities. Data science workflow, its efficiency, its smoothness, is equivalent to capital efficiency in investing, right? The ultimate question here is, does your data science workflow on your teams, in your organization, does it help you drive portfolio effects? Does it help you have many shots on goal at low cost so that you can achieve, so you can get close to the returns possible in this very skewed distribution? New York Times did a survey in 2014, and they asked data scientists where you spend your work, and it turns out that you guys spend more than 80% of your time doing data wrangling. Is that reasonably accurate? Okay, how many of you spend more than half your time doing data wrangling? Okay, how many of you spend less than a quarter of your time doing data wrangling? How many of you have no idea what I'm talking about or just don't want to raise your hand? There we go. The Google papers on machine learning technical debt relate exactly to this. The actual core work that's done around machine learning and data science is a tiny part of the overall system and workflow involved in this, and there is a massive amount of friction and a massive amount of technical debt that just increases that friction over time. It's like barnacles on the hull of a race boat. There's a reason why race boats get taken to dry dock, sanded and repainted before races, because they want to take every last bit of friction out. I don't know what your environments are, so it's difficult for me to give advice about what you can do, but I can tell you what we have done on our end. It's an area we've invested very, very heavily in, because it's a capability that fundamentally improves our ability to drive return from data science across any possible problem domain, right? Given any incoming team resources. We have an environment that supports multiple languages: Scala, Java, Spark, R, Mathematica. If you're comfortable with it, you can work with it, which allows us to work with a diverse data science team. Data is cleaned and organized. There are enhancement opportunities. There's pre-enhancements. There are pre-aggregates. All this stuff is just ready and available for people to grab. By the way, all these orange things are frameworks we've built, some of which, like Spark Records, we've open sourced to solve some of these problems. We have extensive domain-specific languages for both data engineering and data science, model building, deploying, that drop the amount of code that needs to be written or configuration that needs to be done by at least 10x. We have a system for, we call it configuration address storage, which essentially manages artifact generation and sharing. One of the really silly problems in data science is that you're doing something and then you want to tweak one bit, but you want to persist the result. Where do you save it? Well, let me change the file name. Well, now you tweak another thing. Well, let me change the file name again. Ever seen file names with like 3 separate underscore things mentioning effectively dimensions of variation of whatever you're doing because you don't want to recompute it again? Now, what happens if somebody else on your team walked down the same path? Maybe wanted to use data sample the same way or train a similar model, actually not similar, identical model, just purely by accident, right? After all, we all start kind of at the root of a tree. We all may start with, the data for the last 10 periods, and then we sort of branch out in some ways on how we want to work with it and things we want to explore. In our environment, first, you don't have to worry about where things are. You just describe what it is you want. And if somebody has generated it before because they asked for the same thing, it just becomes automatically available to you, sort of in seconds. If it hasn't, then it's going to get generated on demand with all its dependencies, however deep. If one thing changes, if even your random seed into whatever data set you're using for sampling changes, and the data that was generated used a different random seed, you will actually get an appropriate one generated for you. And all that happens automatically. So you focus on the goals of what you want to work with, not exactly how to build it or where it is or how it's saved or any of these things. We evaluate at ad-tech scale, so we need to evaluate very, very quickly in highly customized, highly parallel servers. So no traditional machine learning frameworks for evaluation are fast enough for us. Yet we don't want to have subtle bugs between training and production evaluation. So we try to keep the code as close as possible. There's a framework called MLeap that actually works with Spark that allows you to train things on Spark, as well as TensorFlow, as well as scikit-learn, and actually deploy on the JVM and do very, very high performance predictions, essentially bundling your entire ML pipeline, featurization, so on and so forth, into a big zip file. However, there is no framework that allows you to do data enhancement at runtime. So if you've used very, very sophisticated features or statistically generated features in your models that are not part of a request that comes in, you have to somehow find a way to enhance your data. And there's no good open source framework for doing model ensembling that evaluates at very high performance. So we have one of those. And deployment on these, automatic testing, automatic data collection from ensemble outputs is fully automated. So a data scientist can decide, well, as I'm evaluating this ensemble function, I want to emit the following metrics, taint the event stream with them. Anything that happens following that prediction that leads to whatever decisions and the user actions related to them will be tainted with those metrics and automatically available for analysis. They don't have to lift a finger. My point here is that whatever it is that you are doing, whatever workflow you have, you probably have way more friction than you should. And there's a very human process of learned helplessness, right? Something's hard, you try to solve it, there is no easy way to solve it, so you just kind of learn to live with it, right? It becomes not a pain you're trying to solve, it's a pain you attempted to solve, and then you decide it's unsolvable. So you just learned helplessness, and you sort of would just follow through the high-friction workflow. Don't do that. Find the things that make you unhappy, things that are difficult, they will make you unhappy. Figure out how to solve them. And if you get the engineering team involved, if you get the whole team involved, you usually find ways. Yeah, sometimes it's not cheap. Sometimes it involves non-trivial amount of investment. Or sometimes you'll be able to find projects like ones that we're open sourcing that might help you out. Easy leads to happy people. Happy people are a lot more productive people, holding constant the capabilities of the people. And productive people have a much greater ability to create impact. Also, if you're a Scala and Spark developer and want to help out build some really great open source software, come and talk to me. Now we get to the really hard and interesting part. Evaluations like the due diligence process. You have a high volume deal flow, you think it's pretty good quality, you can generate many, many of these opportunities, but you still have limited bandwidth on what you can invest in and what you can run in production, so now you need to pick. So here's a simple problem. You trained 100 binary click, no click classifiers. You can only evaluate 5 simultaneously in production. How are you going to pick? I'm not the data scientist here. Anybody want to tell me? How many of you are going to pick 5 randomly? Okay. How many are going to pick top 5 based on AUC? Nobody. How many of you don't know what AUC is? Fair enough. Well, the problem with traditional outputs of machine learning evaluation, be it cross-validation, be it whatever, is that they're about predictions, and predictions are not decisions. The example that my team, who's here, helped me think through was that if you're in a minefield and you have to navigate it, and because you're a data scientist, you trained a model that tells you what at coordinate x, y in the minefield, there's a mine, right? So now you have 2 models. They both have AUC of 90%. How do you pick which one to use? Well, if you just look purely at AUC or another metric, whatever it is that you pulled out, cross-validation, etc., they look equivalent. Yeah, but there's a difference in predictions and decisions. Decision is where you're going to put your foot. And the cost of a false positive versus a false negative is very different. False positive is you take a longer walk through the minefield. A false negative is you lose your foot. And that's the difference between the way academia looks at machine learning, where they don't know costs and benefits. It's not that they don't know, I don't care, is that there is no reasonable assumption they can make, and so they essentially make the assumption that all errors are the same. That's the most reasonable assumption when you don't have any other data, right? I'm not dissing academia, it's the logical thing to do, but that's not how the real world works. In the real world works, we don't care about the prediction, we care about the outcome system-wide of the decision made by the prediction. We don't have a single dimension of evaluation, you have many dimensions of evaluation, you're often in direct competition with each other. To give a simple example here, just for any one of our advertisers, you can think of them having a utility function that's, although it's multidimensional, we can maybe reduce it down to 2. One is basically, I prefer to see this as a contour curve. One is essentially, did you spend the money I gave you? And the other one is, did you perform as well as I wanted to, or better? Spending the money is actually really important. It's not just about performance. Imagine going to the bank, giving it $1,000, and in a year they come back to you and say, great news, we got 10% return on 100 of your $1,000 bucks. You say, okay, cool. How do you do on the other 900? Oh, we kind of forgot to put them to work. Well, you wouldn't be very happy, right? So the happy place is this very, very narrow range at the very peak where you meet or exceed the KPI and have to spend all the budget. By the way, there's a big difference here between Google and a company like Swoop. Google has 2 million advertisers. So in AdWords, Google operates on a best effort model, meaning you tell Google how much you're willing to spend, they give you absolutely no guarantee that they'll spend that. Smaller advertising companies can't afford to do that. It's a much easier optimization problem to solve. Smaller companies have to make budget commitments that you actually will spend the budget and achieve the performance. It's a much harder optimization problem to solve. The big problem with this view is that you don't know where on this curve you are, typically until the end of the month. And then has to do with a whole bunch of mechanics of how delivery and accounting of ads and billing and so on and so forth works. But you need to make real-time decisions. So although you're dealing with this multidimensional problem, you have to somehow come up with a real-time proxy. And because you're going to need to rank choices to make decisions, you're going to have to make it a single-dimension one. This in itself, it's a problem we can talk for hours about. But there's also a fundamental approach in how you do this, because you want to do this consistently across all predictions you make, across all decisions you have to take. And by the way, across some decisions you take implicitly in code, because those can be changed. You can make different decisions, or you can deploy an A/B test in code. We actually internally use a synthetic currency. We call it points. And so the unit on the y-axis actually then becomes points per decision. Right? This is what we want to evaluate the system by. Not its ability to predict, but the point outcome per decision. This is important for us because it allows us to compare things relatively, right? And a traditional ML metric, I have absolutely no way to reason about what an X% difference in AUC between two models is going to mean for my system outcome. I don't know. But it also means that you need to develop different tools to see the differences. There's a tool called performance curves, created by a data scientist on our team that we encourage you to copy and use because it's very simple and very powerful. It tries to turn a simple number into a picture you can reason about. There's 4 components here. The yellow curve offers the axes. The x-axis is decisions. Any set of decisions you pick, whatever it is. The y-axis is the utility, points per decision. The yellow curve is the decisions sorted by inverse utility. So if you switch this decision set into an online system and you could just pick one at a time, any one, and at some point somebody will say stop. To generate the maximum value, you'd want to pick them in decreasing order. So if you're the oracle, this is the order in which you'd pick the decisions out of the set. The red curves are essentially they're confidence intervals built from random orderings of the choice set, right? So they tell you what a likely confidence range of an extremely naive system for ranking these things would have done. And the blue is, in this case, a model. Right? And you typically see things like it begins very, very low because there is some randomness in the system, so that you will have some high-value actions that just happen, right? There is no particular reason or predictive reason about it. People just behave in a certain way. But then you would expect it to very, very closely try to get close to the oracle, and then, of course, by definition, everything converges into the same point in the end of the set. We use performance curves in many, many different ways. We use it to debug models. This is, in fact, a picture of the performance curve of the model in the previous slide before we identify and fix the bug in it. Right? It doesn't look normal. It's chunky. We had cases where you can have things which have close AUC but very different performance curves. So again, turning a number into a picture and being able to reason relatively is important here. The area under the curve is your value. The average is the average points per decision you get, and so on and so forth. It's quite convenient. You can also use it to tune chains of decisions together, right? So in this case, we have a situation where 2 predictions end up impacting each other by the decisions the system makes, and we want to optimize the total outcome of the system. And we can look at this naively and say, well, gee, this green thing, the earliest stage, it's tracking the oracle pretty well. So there'll probably be diminishing returns to spending time optimizing there. But this blue thing is probably where we should focus our optimization effort. That's where we should invest our hours. That doesn't solve the problem because we still have the myopia of history. We make some decisions, and they bias the set of observations we have to evaluate against. So if historically we only showed ads 1 through 3, and now we have, so we never showed ad 4, even though it was very valuable, and now we also have ad 5 and 6 freshly added to the system, there's no way for us to figure out how to train something that should correctly show 4 and 5. Again, we can reason statistically. You could try to do some type of transfer learning or case comparisons, but you can never know. So you have to build in exploration, right? Whether you think of it as a reinforcement learning problem, whether you think of it as a contextual non-stationary bandit with mortal arms, whatever framework you think this through, you have to design some way to explore. A lot of the fancy papers that get published on these things are absolutely, the algorithms behind them are absolutely horrible for deployment in a large-scale distributed system. Some of my favorite contextual bandit papers require a cumulative state from point 1. So how do you distribute an algorithm like that? How do you deal with a node that fails and loses some state? It's something that you can't deploy it in theory, but it will be insanely expensive. You can do simple things. You can take some of your production bandwidth and deploy naive predictors, some type of a random predictor, right? You can also invest in infrastructure to do forward testing, what we call replay, right? You can never remove the myopia of past decisions, but you could identify the cases where it occurs, right? But to do this, you need a way to essentially figure out whether, had a different predictor been live in production in a past period, it would have made different, its predictions would have led to different decisions leading to a different system outcome. So you effectively need a way to model the entire decision pipeline of your system and all the choices that move through as data, capture it as part of the evaluation of your system, and then if you have that, you can separate history into a case where a model would have made this, whether the model's presence in the system would have led to the same decision and the same choice presented to users or not. You can evaluate apples to apples in the case where it would have been the same, and you can choose what to do about the other set. You can ignore it, you can reason statistically about it. It lets you control the myopia. It makes you much smarter about understanding the impact of deploying something to production. So the point I can make about evaluation and selection that is, there's hardly enough, especially in these human decision problems, there's hardly enough effort you can spend to actually accurately measure and evaluate reality, because it affects absolutely everything that you do. There's a saying in entrepreneurial circles that if you don't like the options you're presented with, you should make new ones. In data science, I think that's very useful because we very often don't like the options we're given. I'll give you just one example from something we discovered recently. We had an interesting case where we trained, we used two learners, gradient boosted trees with XGBoost and factorization machines with libfm, trained on the same, essentially model structure, same features, and they ended up consistently producing very, very different outcomes. They basically turned into savant models. One could generate a lot of performance, but just didn't consume much budget. And the other one could consume a lot of budget, get users to click, but the clicks were less considered. And so by itself, this probably means that there is a model we can train that does better than either of those, right? There is a model that moves down this Pareto frontier, which, by the way, is not just a line we drew, it's actually numerically tested. It just happens to be linear for whatever reason. Or alternatively, we could say, well, maybe we can exploit the fact that we have savants and actually formulate an optimization problem, a linear program, that actually uses that, which is very different than how the sort of LP, say, in our world, submodular welfare maximization approaches look at predictors, right? If you go to that side of machine learning and data science, they will tell you, yeah, so here's the math, and then plop in your expected value here. Well, let's assume that there's one thing that provides expected values, but that's not the reality. We have many things that can predict, and they predict with different errors. So what do? Do you just take the average of them? Well, okay, that's one approach. But you're not exploiting the degrees of freedom that you have. So in this case, the team is actually in process trying to implement something to exploit the fact that we have a savant that can operate sort of in this region and another one that can operate in the other. So in summary, I really, really want you to think of yourself as venture capitalists, right? Your job is how to spend your time and your teams and your company's resources to invest in things that go to production. You need to generate a great opportunity set of them with enough quantity and quality. You need to evaluate which ones to put you back into. And then you need to make decisions about which of the live models, systems, optimizations, whatever it is, to actually double down on and keep following on, as opposed to take out and replace with something else. Ego makes us want to think of ourselves as really smart. You know, we want to believe that we can just train the one great thing. The reality is, we probably aren't as smart as we wish we were. So we also have to be lucky. And by investing in the kinds of capabilities that drive returns, we essentially increase our capability to be lucky. When you're dealing with a non-stationary, highly complicated, very, very skewed distribution, sometimes you get the best results not by being very smart at how you pick, but by just allowing yourself to pick many, many times, because you know there's things out there that will drive a lot of value for you and your team and your business, but you may not be sure which ones they are. This is all what I wanted to share today. I'd love to answer some questions.
Did you just stun everyone?
I guess nobody wants to be a venture capitalist. Come on, you fly first class. Everybody's very nice to you because you write the multi-million-dollar checks. By the way, that part doesn't quite apply to the analogy, unfortunately.
Anyone? Wow. They interrogated the first two people.
They're in the back.
So I'm a big fan of analogies. Do you see any weaknesses to this analogy other than the first class and multi-million-dollar checks?
I don't. I mean, it is a portfolio maximization problem, right? What we're optimizing for is our time and how do we spend it. A software engineer building, a web app can have a very predictable output of an hour of extra work, tweaking some database table to add another form field to a web page. Some parts of data science workflow can have very predictable outputs, but when it comes down to, building models, evaluating models, feature engineering, optimization, much of our work has a very, very, very unpredictable outcome that is most definitely not a Gaussian.
So on sort of a meta level, how did you decide that it was the right thing to do to invest in the infrastructure that allowed those quick iterations? There's a lot of infrastructure on that slide with all the open source projects and so on, right? There was a big startup cost to do that.
Yes and no. I mean, we converge, right? As most things in startups, you don't say, gosh, I'm going to do no data science until we have all of this. You basically start doing data science, and you find out where the pain is, and you just meticulously start, removing friction. So back in the analysis I did of angel portfolio returns, at some point I wanted to ask myself a question. Clearly there were portfolio effects, right? Anytime you have a highly skewed distribution with a long tail, you're going to have portfolio effects. So the interesting questions were, okay, so how big of a portfolio should you have, assuming this distribution across tons and tons and tons of angel investment portfolios, to give yourself a guarantee, with reasonable confidence of a return greater than X, right? And based on the distribution I showed where, again, the median is very close to 0, the mean is about 3.2, you needed about, I did Monte Carlo studies, and you needed about a portfolio of 50 to get past the 1.5x return, and to get comfortably above 2x, you needed a portfolio of over 100. So to me, this basically means that mechanically, unless you're an oracle, you need a system that is fundamentally designed for high volume in production experimentation. Because again, if you're dealing with image classification, I envy you. you have a gold standard of truth. You can scale gajillion amounts of processing and experiment up to the wazoo. But when you're dealing with humans in all counterfactual, your most precious asset is your limited production testing bandwidth. The other reason why Google outperforms everybody and Facebook is getting close is they simply have an insane amount of volume, which allows them to run many, many, many more experiments in production. And that capability is sort of irreplaceable. You can be smart about it. There's old math from sort of lean manufacturing of essentially how do you smartly explore a set of many variations without sort of going through the combinatorial set. But the reality is they had much more precise measurement. When you combine the errors in measurement, it becomes very, very dangerous to start applying fancy math because you never know to what extent a deviation you're seeing is due to fancy math versus a change in reality. There were graphs that I just didn't have time to show that would show a random model changing its performance for a period of time by 3x, by 300%, and then dropping back down. Was it just random people? Was it some change in the world which we're unaware of? I mean, just over a period of a few days. But it happens. And you need to be able to detect it. So fundamentally, it's not that you don't try to be smart. It's that you can't count on being smart and right at the same time. Does that make sense?
One more.
So we're a little bit lower on the totem pole. What would be your recommendation for kind of convincing people that removing that friction is a really important piece? To your point, getting some of those data elements more well-defined, because they are that capital investment, and that capital investment we need to kind of demonstrate a value for if you want it, but it's really hard to demonstrate, well, if we make this investment, we'll get something out of it, because to your point, it is very random.
It's actually the simplest argument. It's math, right? If you accept the fact that you are dealing with a highly skewed distribution, then that has a meaningfully good mean, right? Meaning, in your business problem, you can reasonably believe that machine learning and artificial intelligence can create significant impact, right? But it may not exactly be obvious how, right? Or even if it's obvious how, it may not be easy to do because the problem's hard, right? Then it's very easy to posit the problem as purely a math problem. Then it becomes, okay, so this is your distribution. How do you get to the mean, right? You can't say, oh, well, I'll just, invest in Uber. Well, great. Every investor wants to say that. Every venture capitalist that raises money from limited partners as the people who invest money in venture capitalists says that they're going to generate a great return. But the reality is that most venture capital firms as a whole actually barely return the money of their investors. So in that type of environment, again, it's not that you don't try to be smart, but fundamentally you have to be able to try many, many, many things safely, meaning without killing your business or without hurting your business.
Awesome.
Thank you so much.
Oh,
It's the break now. Oh,
okay. We'll give you one more. Make it a hard one.
How you
Hi.
doing? Can you talk a little bit more? So the analogy of a portfolio approach to data science makes a lot of sense. But ultimately, from a customer standpoint, it's very clear what the KPIs are in this particular industry you're involved with. Can you talk a little bit about the introduction of the points mechanism that you guys had to invent as a means to get to the customer KPIs? And at which point do you, or how'd you go about fine-tuning that points currency idea such that it tracked well with the actual customer KPIs?
It's an excellent question, and I wish I could give you a clean and wonderful answer that makes me look really smart. The reality is a lot nastier than that. Customers actually don't understand their KPIs. Customers at any one point have a KPI. They've been known to change it mid-campaign. They've been known to introduce a second KPI mid-campaign. they've been known to acknowledge that their KPI makes absolutely no sense for their business, but is easy to measure, or the only thing that a system allows them to measure. I'll give you an example. One of our biggest clients who spend millions of dollars with us in a performance advertising campaign is measuring us on click-through rate. So the measures on how they pay us per click. So the measures on how fast we spend their money. Now, the reality is we're actually optimizing for multiple objectives for them. We have to clear this sort of checkpoint metric, or otherwise all kinds of red flags get triggered in their own analytic systems. But in conversations with them, we know what they really want to do, which is certain things that happen post-click with the engagement of the user with their site. And that's what we're actually trying to accomplish for. But now we're sort of doing it. We're running a race with our legs hobbled together because we have to be spending their budget at a certain rate, yet at the same time, only generate high quality enough clicks to do the thing that we know is right for them, because sometime, hopefully this year, they will wake up and go, oh, gee, we finally implemented system X, which allows us to now measure what we really wanted to measure, which we couldn't measure, and therefore we're going to start evaluating on this. So for us, the important insight was that we needed to divide and conquer. We had to separate the problem of how do you assign real-time reward from the problem of how do you build a system when where you have a consistent system level, impact level optimization objective, which is points. And our very first implementation was idiotically simple. We basically we gave our ad operations team, who deals with the sales team and deals with the clients, a whole bunch of configurability to assign points to various user behaviors on a per campaign basis. And we sat down with them and we educated them about various knobs and switches. And then, instead of putting any ML to help them with that, we built some tools to help create insights into when points are assigned poorly. So it's very difficult to go to somebody who is 20-some-year-old marketing degree person who barely understands advertising and sort of talk to them about trade-off functions and optimization under competition and the impact of rising point values here and how that's going to trigger everything else. But what it's easy to do is if you give them two choices, two sort of situations, say, look, here's situation A, system does X, produces the following outcomes. Here's situation Y, system does something else, produces other outcome. Which of those two would you prefer? It's usually trivially easy for them to go, oh yeah, A. It's because, well, guess what? A generated 40% fewer points than B. So you may want to rethink about how to configure points. And we've gone through several iterations of kind of tuning the tooling around this to a point where, again, it's working pretty well, hence us being able to operate reasonably close to Google, which in ad tech, again, is fairly unheard of, given that we don't have search, we don't have people searching at the moment, we don't have user queries, we most definitely don't have the resources that Google has. I'm sorry I don't have a more clean and applicable problem, but the core insight is that you have to give yourself degrees of freedom to do the right thing in your system. And that sort of requires a business impact-oriented, unidimensional real-time metric. It may have absolutely nothing to do with ML metrics, right? And so since that is an absolute requirement for doing anything, then you can take that as a given and say, okay, well, I'm going to work as if this is provided, and then separately, I'm going to figure out now how to deal with the problem of appropriately assigning reward in near real time or in real time to, whatever can happen, which is a very hard problem. Thank you again so much.